In a previous video, we looked at proposition 315, which says that the matrix A is invertible if and only if the reducer echelon form of A is the identity matrix, so A is row equivalent to I. In addition, we can find the inverse by augmenting A by the identity matrix and finding the reducer echelon form, so sort of reducing that A augmented with the identity, and we would get the identity in place of A and A inverse in place of the identity. What we'd like to do in this video is actually prove this proposition. To begin, we want to introduce a concept of an elementary matrix, which is one that is obtained by performing a single elementary row operation on an identity matrix. So let's look at some examples. If we started with the identity matrix, we'll do this for the 3 by 3 case, but this would work for any square identity, square matrix, any size identity matrix. One of our elementary row operations is interchange. So for example, we could interchange rows 1 and 2, and we would get an elementary matrix, 0, 1, 0, 1, 0, 0, 0, 0, 1. So this is an example of an elementary matrix. Maybe we would call that, I don't know, E1. So let's just put a few examples over here. 0, 1, 0, 1, 0, 0, 0, 0, 1. Let's do another example. So let's get rid of this one. And maybe we will do a scaling example. So what if we took, I don't know, row 3 and scaled it by 3? So maybe we did 3R3. We would get the matrix 1, 0, 0, 0, 1, 0, 0, 0, 3. So that's an example of an elementary matrix. Maybe I'll call that E2. So just giving a few examples here. And let's do one more for our row replacement. So again, we'll get rid of this one. So maybe we will do row 3 minus 2 row 1. So row 3 minus 2 row 1. So that gives us the matrix 1, 0, 0, 0, 1, 0. Let's see, 0 minus 2, and then 0, 1. So maybe we'll call that E3. So just a few examples of these elementary matrices. These are going to be important for the proof of that proposition. So I wanted to introduce them here. We will also see these in other parts of the course. So we'll keep this kind of concept in mind. So a proposition here, if an elementary row operation is performed on an M by N matrix A, the resulting matrix can be written as EA, where the M by M matrix E is created by performing the same row operations on IM. Just as a reminder, this is the M by M identity. So let's take a look at some examples. I'll just make up a matrix A here. So 1, 2, 4, 0, negative 1, 3, 2, 1, 1. Okay, so there's a matrix A, and this says that I can perform an elementary row operation on A by sort of thinking of it as a matrix multiplication by an elementary matrix. So let's go back to these matrices here. Let's try E1 times that new matrix that I just came up with here, A. So if I did E1 A, so E1 was an interchange, right? An interchange between rows 1 and 2. And so this will be 0, 1, 0, 1, 0, 0, 0, 0, 1. And we go through this matrix multiplication. Okay, and you could see that we're going to get 0, negative 1, 3, 1, 2, 4, 2, 1, 1. So you can see actually we do just get the original matrix A with rows 1 and 2 interchanged. Let's do one more example. Let's do the replacement example. So E3. So maybe we'll try E3 times A. Okay, so we have E3, 1, 0, 0, 0, 1, 0, negative 2, 0, 1. Multiply that by A. Okay, and the result here, we just go through carefully. So we get 1, 2, 4. Row 1 didn't change. Row 2 doesn't change. But then we get to row 3, and you can see we're going to do negative 2 times each element in row 1 plus whatever we had in row 3. So we'll have negative 2 plus 2, so that's a 0, and then negative 4 plus 1, so negative 3, and negative 8 plus 1, so negative 7. Squeeze that in there. And so you can see that this is essentially the same as taking our matrix A and doing that, that replacement, that row 3 minus 2 row 1, and you can double check that. Okay, so we could prove this particular proposition slightly more generally, but hopefully seeing a few examples convinces you that this will work. So what this does for us is it kind of takes those elementary row operations, and instead of them being sort of their own operation separate from other things we've been doing with matrices, they kind of become this matrix multiplication. So we can view elementary row operations as matrix multiplication, where we multiply this special elementary matrix by whatever the matrix is that we're doing the row operation on. Next one, each elementary matrix E is invertible, and specifically the inverse of E is the elementary matrix of the same type that transforms E back into I. So if we wanted to look at the inverse of, let's go with E1 from earlier. So that was the interchange of the first two rows. How would we transform this back into the identity? I guess we'd have to just re-interchange the first two rows again. So we would, get the same elementary matrix essentially. And if we tested that, let's multiply these two things together. So multiply this thing by itself essentially. Hopefully it does what we want it to do, and we just get the identity. Again, as you're going through this, it's maybe starting to become clear why this works, and it will indeed work. So an interchange, the elementary matrix for an interchange will essentially always be its own inverse. What about let's do the scaling example. So E2, what did we do for E2? Scaled row 3 by 3. So 1, 0, 0, 0, 0, 1, excuse me, 0, 1, 0, 0, 0, 3. How would we get this back to the identity? I guess we'd have to scale row 3 by a third. So 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, a third. And you could test this out. If we multiplied these two things together, we would indeed get that original matrix back. And then what about the row replacement example, E3? So we did R3 minus 2R1. So that was 1, 0, 0, 0, 1, 0. Negative 2, 0, 1. How would we return this to the identity? I guess we'd have to do R3 plus 2R1. So the inverse of this, would be 201. And again, you could multiply these together and just double check that this would indeed return us back to the identity. So each of these is invertible, and its inverse is whatever would transform it back to the identity. So let's go back to our proposition now. We've got a few tools in place and a few other sort of propositions along the way, and let's take a look at the proof of this proposition. First of all, just sort of reminding ourselves the wording here. This proposition includes the if and only if wording. So that tells us that this proposition, is sort of going in both directions. Not only do we need to prove that, if a matrix is invertible, then it can be reduced to the identity, but also the other way. If a matrix can be reduced to the identity, then it is invertible. So let's make sure we prove both of those directions here. So suppose A is invertible. So we'll go that direction first. Suppose A is invertible. Then, since the equation AX equals B has a solution for each B, that was another proposition we saw, has a solution for each B, we know that A has a pivot position in every row. But since A is a square, since A is an n by n, or square matrix, having a pivot in every row means that, so since A is an n by n, a square matrix, it must have a pivot position in every diagonal position, and thus be row equivalent to I. Okay, so that's sort of the, if A is invertible, then it is row equivalent to the identity matrix. Let's now go the other direction. So, fresh page here. So now, suppose A is row equivalent to the identity matrix, then it can be row reduced to I, to the identity. So there must be a sequence of, so there is a, we'll say, set of elementary matrices we'll say E1, E2, however many of these we need to reduce this to the identity. So maybe we'll just say there are P of them through a EP, such that, so each time we perform an elementary row operation to get A down to I, we can think of that as multiplying on the left by one of these matrices. And so, we can say that first we would perform E1, whatever the operation is corresponding to E1 on A. And then on that new matrix, whatever E1A is, we could perform E2, and then E3, and just sort of continuing along there until we've done all P of these operations, and eventually we would get to the identity matrix. But we also know that each of these, since each elementary matrix is invertible, we can multiply on the left by each of their inverses. So we can take EP, this whole product, down to E1 times A, which we know equals I. I'll leave a little space actually, equals I, and multiply first by EP inverse. So EP inverse on the left. And when I sort of reassociate that matrix multiplication, EP inverse times EP will be the identity. And then I can multiply by EP minus 1 inverse. And we'd pair that with EP minus 1, which is sort of in this dot, dot, dot here, and get the identity. And we keep doing that until we go all the way down to E1 inverse. And so what we see here is that, and I'll also perform each of those multiplications on the left-hand side. So what we see here when we sort of simplify all this down is that A is just equivalent to E1 inverse, dot, 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 down to EP inverse times I, which is just that. Okay. Now it turns out that so we know this is the product of a whole bunch of invertible matrices. It turns out that the product of invertible matrices is invertible. We don't actually need that in its full generality here, but that does help. So we know that A is invertible in this case. But furthermore, let's take a look at if we multiply A, which is now this, this E1 inverse down to EP inverse. If we multiply that by on the right, it doesn't matter actually, left or right, by EP down to E1. Let's do that on both sides of this. So E1 inverse down to EP inverse, EP down to E1, what we see here is that we can have this pairing thing. So EP inverse times EP is the identity, and then all of these are going to pair up until we've sort of paired all of these. So we get the identity. So this whole thing equals the identity. So what does that tell us? It tells us that this thing, this product of these elementary matrices, is A inverse. So let's go to another fresh page here. So just to reiterate, we had A times this product, EP down to E1 equals the identity. So that means by definition that this product, EP down to E1, is equal to A inverse. But EP down to E1 can be thought of as EP multiplied down to E1 times the identity. And so we can think of this left-hand side here as performing the elementary row operations that correspond to E1, E2, up to EP on the identity. And so this is, essentially what we're trying to show. I'll put this box here to represent the fact that we are done with this proof, because what have we shown? We've shown that, we can reduce A to the identity matrix. But furthermore, those same elementary row operations, E1 through EP, that we perform on A to get it to the identity, can be performed on the identity to get it to A inverse. Okay, so a nice proof here, and also sort of along the way, we've introduced the concept of elementary matrices, which again are potentially going to come up a little bit later as well.